By this point in econometrics, we know a lot about what OLS is supposed to do when the model is well specified and the sample behaves nicely. But real empirical work is usually messier than that. A regression can be perfectly estimated and still be misleading because the functional form is wrong. A variable is measured poorly, the sample is selected in a biased way, or a few odd observations are driving the result. So this episode is really about learning where good econometric technique can quietly go off track. Why is this topic so important? Because many serious empirical mistakes do not come from a broken formula. They come from asking the right estimator to solve the wrong design problem. If the model shape is wrong, OLS will faithfully estimate the wrong shape. If the data are missing in a systematic way, OLS will faithfully estimate a selected sample instead of the population you care about. So the practical message is simple. Before you trust a coefficient, you have to trust the data construction and the specification choices that produced it. Start with functional form misspecification. This is basically an omitted variable problem, where the missing variable is really some function of a regressor you already included. Maybe the true relationship is nonlinear, but you forced it to be linear. Maybe the right model uses logs, or an interaction or a squared term, and you left that out. In that case, the model is not wrong, because it forgot a whole new economic variable. It is wrong because it imposed the wrong shape on the variable it already had. The crime example from the lecture shows this nicely. A specification without quadratic terms looks fine at first glance, but once squared terms are added, several coefficients move a lot and the fit improves. More importantly, the interpretation changes. Variables that looked purely negative in the linear model now show a deterrence effect only at higher levels, with positive linear terms and negative quadratic terms together. That is exactly the kind of mistake functional form misspecification creates. The first model was not just less flexible, it was telling the wrong story. One popular diagnostic here is reset, the regression specification error test. The idea is straightforward. Estimate your model, take the fitted values, then add nonlinear functions of those fitted values, like y hat squared and y hat cubed, back into the regression. If those added terms matter jointly, that is evidence your original model left out some nonlinear combination or interaction. Reset is useful because it gives you a warning light, but it does not tell you exactly what to add next. It says something is missing, not what the correct repair is. Sometimes the choice is between two completely different specification families, like levels versus logs. Those are non-nested models, because one is not just a restricted version of the other. In that setting, you can temporarily include both levels and logs in a larger regression, or use fitted values from one model inside the other to see whether the competitor contains extra explanatory power. But even then, you want to stay humble. Rejecting one model does not prove the other is the true one. It may just be the less bad candidate among the models you tried. Now move to proxy variables. Suppose a relevant regressor is not observable at all. A standard example is ability in a wage equation. We cannot measure ability directly, but we might observe something related to it, like an IQ score. That related variable can serve as a proxy. The goal is not to perfectly recover the hidden regressor. The goal is to soak up enough of its variation that the coefficients we really care about, like education or experience, become less biased than they would be if the hidden regressor were omitted entirely. But proxies are not magic. They help only if they are actually related to the missing regressor in the right way. And even then, the proxy coefficient itself usually does not have a clean structural interpretation. It is carrying both the effect of the missing variable and the imperfection of the proxy relationship. So the right way to think about proxies is defensive. They are often useful for protecting the main coefficients of interest, but they do not turn a missing variable problem into a perfectly observed one. Measurement error is different from a proxy problem. With a proxy, the stand-in variable is related to the true variable, but is not literally the same thing. With measurement error, we are trying to observe the same thing, just badly. If the dependent variable is measured with error, and that error is unrelated to the regressors, the main effect is extra noise in the regression error term. That makes the estimates less precise. Standard errors get larger, t-statistics get weaker and significance becomes harder to establish. But the slopes do not have to be biased in that clean case. Measurement error in an independent variable is much more dangerous. Under the classical errors in variable setup, the observed regressor equals the true regressor plus noise. In that case, the estimated slope gets pulled towards zero. This is attenuation bias. And the crucial point is that bigger samples do not automatically fix it, because the problem is inconsistency, not just imprecision. If a regressor is badly measured, the estimated effect can look smaller than it truly is no matter how much data you collect. Next comes missing data and sample selection. Not all missing data are equally bad. If observations disappear completely at random, the main loss is sample size and precision. If missingness depends only on observed X variables, OLS can still be okay, although your interpretation may only apply to that observed range. The really dangerous case is when missingness depends on the dependent variable or on the unobserved error. Then, the available sample is systematically different from the target population, and OLS inherits sample selection bias. Think about estimating returns to education using only employed college graduates with wage data. That sounds natural, because wages are only observed for people who are working, but employment itself is part of the selection process. If the unemployed are excluded, the sample is no longer representative of all college graduates. The wage equation is then describing a selected subset, not the broader population. The right fix is not a better standard error. The right fix is a better sample design, ideally one that starts from all college graduates and then records employment outcomes. Finally, outliers and influential observations. OLS squares residuals, so unusually extreme points can have a disproportionate effect on the fitted line. Sometimes that is because of a data entry mistake. Sometimes it is because the observation really comes from a different underlying population. Either way, you do not want to pretend the issue is not there. A sensible workflow is to inspect strange points, correct clear data errors when justified, and often report estimates with and without influential observations so readers can see how sensitive the conclusions are. So the real lesson from this episode is that empirical credibility lives upstream from the regression output. You need to think about functional form, missing regressors, noisy measurement, missing observations, sample selection, and influential points before you get too attached to a coefficient table. Econometrics is not just about running the cleanest formula. It is about making sure the formula is being asked to solve the right problem on the right data. Data and specification issues are where applied econometrics starts to feel real, because this is where theory meets messy evidence. The payoff is that once you learn to diagnose these problems, you stop treating regressions as automatic truth machines. Next, we move to dummy variables, which look simple on paper but open up a lot of practical modeling power.